Hi there, let's get started. Welcome to the project demo of Team 29. So in this video, we'll be showing you a brief demo of our Thought ID, which will help the user to authenticate himself to the smartphone using his brain waves. So before jumping on to the actual demo, I want to highlight a few things that are unique to this project. So the machine learning algorithm which drives this Thought ID is implemented by our team, and that is one of the unique things. And the cloud server that we are using for this application is the actual server that is hosted on Amazon Web Services EC2 instance. And this particular app also has two modes, where first mode is the typical regular user mode, where he just enters his user ID and then he'll get authenticated. And it also has an expert mode which will help us to show you the effort that has gone into building this whole application. So let me go ahead and show you the normal application of a typical user, where he'll be presented with this first screen that you can see on this emulator right now, where this first screen expects the user to enter his user ID, and for this particular instance we have taken it as 1. And once he clicks on proceed, he'll be taken to this screen where we'll be giving him instructions which says that in the next step we'll be showing him a YouTube video which will help him to relax while we collect his brain data. But for all practical purposes, we are collecting the brain data from the SD card that is on the emulator. So once I click on this continue button, the user is getting showed of this video which will help him to relax while we are actually reading his brain data from the SD card. So once we got the data, this application is trying to post the data to the web server. As you can see, this terminal is the EC2 instance terminal window, and this is the log. So as you can see, we got a hit from the application at the same time when the application tried to post, and our cloud server says the brain data that is sent from the mobile application is actually of the user 1, which we used for the training. So the cloud server execution time, the whole time, including the network latency and the execution, is 1941 milliseconds. And we also include the battery level just to show that we can even adapt if the battery is low. So in the next step, we'll be explaining you the technicalities behind this implementation, after which we'll be showing you the expert mode.
Now that we have seen how our app functions, let's see how exactly the machine learning parts work on behind the scenes. So the dataset that we're working with is a 64 channel 160 hertz dataset, which basically means for each user we have 64 channels of data which was collected at 160 hertz. This dataset has just amplitude values which cannot be used directly to distinguish users from one another. So for that, we had to do some sort of transformation before the machine learning could even be applied. For this transformation and pre-processing, we followed a research paper which was trying to do similar stuff, that is distinguishing users based on the EEG data. What they did, and that is what we did later, is just worked with one of those channels, that was OZ. Then for this channel, we averaged this data out to smoothen it out. So for smoothing, what we did was we took the average of 50 continuous samples. That's like a slow smooth out that we did. Once we had this smoothened data, what we had to do was to split it into multiple smaller chunks, time chunks. The reason for doing this is the logical next step is to convert this into a frequency domain, but as we know, for the way to do this would be Fourier transform, but we could pass a Fourier transform function any n length time series data. It would still return us the same data in the same frequency domain, the same frequency range, to be precise. But we needed multiple samples for our model to work. So what we did is that for each user, we created 500 millisecond window, and we just slid it one sample, just one sample by one, and basically creating multiple 500 millisecond samples from 1 second of data. For each of these windows, we then create took the fast Fourier transform, thus changing it into a frequency domain. Then we passed a low pass 60 hertz filter, which basically removed all the frequency information that was above 60 hertz. Then for this remaining, for the 0 to 60 hertz data, we split it into 5 different bands. That was alpha, beta, gamma, delta, and theta. These bands represent different frequency ranges and are said to be really powerful in detecting users from one another. We just didn't took these simple mean of these values. Rather, what we did was we took the entropy, um, standard deviation, and mean. So thus, for each of these 500 millisecond samples, we represented it by a 15 length feature vector. In the end, um, for each users, as we had roughly a minute of data, what we ended up with was roughly 9,440 samples. So now the way the machine learning model works is by differentiating the data that is stored on the server versus the data that comes in from the mobile system. So to kind of understand what it does is um, it has some data stored on the server and it has some data that the mobile system sends it. And what we do is we merge both of these data sets together, set the labels for the first part 1 and set the labels for the second part 0. Now, if the two users would have been the same, then the model won't be able to differentiate between the two, and thus the prediction accuracy would be pretty low, near about zero point 0.5, near about 50%. On the other hand, if these two users were really different, then the accuracy would be really high, somewhere near 90 or maybe 100%. So this is what we did. We tried our modeling with multiple different models. We tried many decision-based tree methods such as random forest, but for our purposes, only these following worked really well. As you could see from our experiments over here, these are average experiments run over 100, run 100 times, and these are the average results. As you could see, these models performed really well if the users were the same, and similarly, if the users were different, they were able to very nicely distinguish between the two. As for our experiments, naive Bayes was the model that worked really, really well and was able to say if the users were similar and also distinguish between different users. Worked really, really well for us.
Hello users, till now we have seen about the technicalities in the machine learning part of the app. So let's briefly go into the expert mode in the app. The expert mode will be used for the authentication and authorization of the app. So let me first toggle the expert mode on. So the first text box is having the user ID who is trying to get authenticated, and the second text box has the user ID whose data will be sent into a server for authentication. So let me enter 1 in the first text box and 2 in the second text box. So let's now try to send the second user data while the first user is trying to log in. Okay, let's proceed, and a video is being played and the brain data is getting read. We would expect our cloud server to deny the access because he's not the actual user. The data is getting posted to the server. So as expected, the machine learning algorithm has correctly responded, telling that the user whose data that we sent doesn't belong to the actual user who's trying to log in.
Hello users, so now we will be testing our app with the Fog server. The Fog server is hosted on this MacBook Pro. We are using an Apache XAMPP server here. So on my left I have the terminal of the Fog server and on the right I have the terminal of the cloud server. So first let me start the Fog server on the left. So the Fog server is getting started, and yes, it has been started. So let's test it using the Fog server. I'm selecting the Fog server option, and we have to give the IP address of the Fog server as it is dynamic and it will be changing. So let me give the IP address, and I'm trying to log in. So the video is being played and the data is being collected. Now the data is getting sent to the Fog server because the user has explicitly mentioned it as his choice of server. The Fog server has the same logic implementation as that of the cloud server, and it is also in the same network as of the device. So we got the naive Bayes as true, and the execution time is 3,710 milliseconds. So
So guys, let us see the adapt option of this application. On the right, I have the terminal of the cloud, and on the left, I have the fog server terminal. So we can see that both the servers are started, and we would test this app with the adaptive offloading algorithm. So let me first select the adaptive offloading option. I'll give a user that would be my user to be authenticated, and I would be required to give the fog server IP address. Yeah, so by selecting the next option, if the user selects the adaptive offloading option in the expert mode, then we would also be needing to provide the fog server address. So that's what we did here. And going back to the next thing, the video is being played and the data is being collected. So the application will try to find the network latency by connecting to the cloud server and the fog server, and select the server that would send back the response faster. The application would consider both the execution time on the server and the network latency and determine which server to adapt. So as we can see, the fog server has been selected as the execution time there is 353 milliseconds. So we can see on the left that the the app tried to hit the fog server, and the machine learning algorithms have been run on the fog server. The project requirement document says that we need to consider the phone's battery percentage while doing the offloading. So now I'm going to demonstrate what would happen if the phone's battery percentage level is less than 25%. Our algorithm will directly connect to the fog server if the battery percentage of the phone is less than 25% instead of taking the latency of the cloud and the fog servers. Let me change the battery percentage uh, in the phone in the emulator to 20 something which is less than 25%, and see and check how this offloading algorithm works. So like I'm entering the user to be authenticated as one, I'm selecting the offloading option and giving my fog server input. Yeah, so I'm proceeding with this. Let's continue. The brain data is getting collected and it will be posted to the server. So as we can see on the left terminal, the app is trying to hit the fog server. So the fog server was selected actually. The execution time is 4027 milliseconds and the battery level is 21% here. So and by this we have completed the first three phases, and we also completed the first three tasks in the phase 4. So we have also computed the execution times of both the cloud and fog servers, and we got them as 750 milliseconds on the cloud and 810 milliseconds on the fog servers. So we are yet to implement the power consumption of the smartphone when using the fog or the cloud server, and also the comparison of the servers. So we would be doing the last two tasks in the phase 4 in the coming week. So this is our app execution, and thank you.